So in this question, we're looking for a kind of light to completely ionize a hydrogen electron in the ground state. Oh, so now we're talking about a photon coming in and exciting it from here to here, which will require 13.6 eV. Well, 13.6 eV. eV on the bottom, joules on top. 1 eV is 1.6 times 10 to the minus 19th joules, which gives us 2.176 times 10 to the minus 18th joules. And we are looking for the wavelength. So if E equals HF equals HC over lambda, then lambda, the wavelength, equals HC over E. So that is 6.626 times 10 to the minus 34th, all times 3 times 10 to the 8th, all over this answer, which was 2.176 times 10 to the minus 18th joules. And that gives us a wavelength of 9.135 times 10 to the minus 8th meters. Going to our chart, our identification chart, which I didn't bring over, but was in the lesson previously. Oh, let's go to it. It's over here. So let's see. We have 9.125 times 10 to the minus 8th. 9.125 times 10 to the minus 8th. So that's meters times 1 meter is 10 to the 9th nanometers. So that's 91.25 times 10 nanometers. So we can see again, that's too short right there. So it's got to be, these are all too long. So it's got to be shorter than violet. Shorter than violet. So looking at our choices, that's out, that's out. Visible UV, that could be violet UV. Let's go a little further. Now 9.125 times 10 to the minus 8th is really times 10 to the minus 7th. Because if we had 3.16 times 10, 3.18 times 10 to the minus 8th, that would mean it's it's closer, we would round that to 10 to the minus 7th. Because it's closer to 10 to the minus 7th than it is 10 to the minus 8th. It's closer to a power of minus 7 than a minus 8. So looking at it from that perspective, we could say this is around a negative 7. So we're definitely out here. An X-ray is 10 to the minus 9th, so that's out. 10 to the 7th to 10 to the 8th seems a lot closer. It's not all the way down in the 7s. It's not quite that large yet. So probably the best answer is ultraviolet. And that is choice D.